Welcome to Mathematics. Today we'll be solving the Pearson Edexcel IAL January 2023 paper of Physics Unit 4. In the first question, we are given a question about the structure of protons and neutrons, and we have to deduce the quark structure for them. Now for protons, we know that their charge is plus 1e, and protons are made from 3 quarks. So if I have two up quarks, so I have plus 2 by 3 plus 2 by 3, this will be 4 by 3. Then I can add a down quark to it, minus 1 by 3. Here I'll get a charge of plus 1e. So a proton will have two up quarks and one down quark. So this. So C is the answer. You can also check for neutron. Neutrons have a charge of 0. So if I have one up quark, which is plus 2 by 3, and two down quark, minus 1 by 3 each, then this is a neutron. So I have two down and one up. This matches. C is the answer. Now in question 2, we are given that a centrifuge that rotates at 1500 revolutions per minute, we have to find the angular velocity for it. This is the angular velocity. It's 2 pi n divided by t. N is the number of complete revolution. In this case, it's 1500, and the time is 60 seconds. So between our options, if we look at them, option D will be the correct answer. Now in question 3, we are given element X, which emits an alpha particle to produce this nucleus over here. We need to find the correct Nucleon structure of element X. So we had element X over here, and it decayed to element Y through alpha radiation. So this is the equation. On the left hand side and right hand side, the mass number and atomic number will be balanced. So 91 plus 2 is 93. And on the top we have 233 plus 4, which is 237. So this is element X over here. The number of protons will be 93. So option A and D are out. Now I have to look for the number of number of neutrons. In this case, the mass number is 237. So number of protons plus the number of neutrons add up to 237. We know that the number of protons is 93. So the number of neutrons is 237 minus 93, which is 144. So the number of neutrons is 144, not 237. 237 is the mass number. So the total number of neutrons and proton is 237. Now in question 4, we are given a magnetic field directed into the page. So this is the magnetic field into the page. We denote anything that's going into the page with crosses. So think of it like a dart. A dart has a pointy end on this side and a cross looking thing on the other. So if I see the dart from this point of view, so the dart is moving like this, I'll see the back of the dart. So this is the back of the dart on this page. If I look at this dart from here, if it's coming towards me, I'll see a dot. So when something's coming out of the page, we represent it with dots. So we have a magnetic field over here like this. Now since the radius is decreasing as we go from Y to X, the particle is moving from Y to X. If it was moving from X to Y, it would have started with a large radius and then ended up with a smaller one at y. So the radius, when the radius of the curvature over here is larger, that's the starting point. As it keeps on moving, it loses its radius of curvature, and the radius of curvature decreases as we move on, or as the particle moves. Now we have to use Fleming's left hand rule to find if it's a positive charge or a negative charge. So we use our Fleming's left hand rule over here with our hand. The thumb represents the force, the index finger represents the magnetic field, and the middle finger represents the current. Current over here is the direction of motion of positive charge. So I'll look into this curvature. The force is towards this direction. This is the force. The magnetic field is into the plane. So I'll put my thumb like this, put my index finger into the page. So I'll have my thumb like this, the index finger pointing into the page. The current will come out to be in this direction. So the current comes out to be in this direction. It's opposite to the direction that y is moving in. If I use Fleming's left hand rule and place the magnetic field and force, and the current comes out to be in the opposite direction, we can be sure that it's a negatively charged particle. So from beforehand we were sure that it's moving from y to x, so option C and A are not the answers. And we know that it's a negatively charged particle, so positron is not the answer, so it must be an electron traveling from y to x. Another shortcut you can use for questions like this, where you have a charged particle moving like this, somewhat in a spiral. If it's a negative particle, you can use the right hand rule. It basically serves as flipping your middle finger to the opposite side, since if the negative charge is moving to the left, if this is a negative charge moving to the left, the current is to the right. So the direction of motion of a negative charge is opposite to the direction of current. So for negative particles, you might use the right hand rule to find the direction it moves in faster, or you can use it in this case as well. We see that it's not the direction of current is opposite to the direction of motion of the particle, and if you use the right hand rule, you'll see that the current is in the direction of the motion of the particle. If I use the right hand rule and everything seems to work out, then it must be a negatively charged particle. Now moving to question 5, we are given a question about which of the following statement is not a valid conclusion from alpha particle scattering experiments. Now the alpha particle experiment is basically shooting alpha particles at a thin gold foil. So in gold there are gold atoms over here with its nucleus. Now if I shoot alpha particles at this, the alpha particles move away. Most of the alpha particles go straight through the atoms. The ones that are close to the nucleus moves away. From this we can conclude that most of the atom is empty space, since most of the particles will just go right through the atom. We also know that most of the mass is concentrated in the nucleus, because when alpha particles are going close to the nucleus, it shows a lot of deflection, which wouldn't be the case if the mass was not concentrated. Option 3 is not right. If it carried all the charge of the atom, if the nucleus contained all the charge of the atom, it would end up being neutral. since we know that there are atoms are usually neutral, there are electrons going around and a nucleus in the middle. If we if they're telling us that all of the charge of the atom is in the nucleus, they also mean that this negative charge is also in the nucleus, which would be wrong. So this is the answer. This is not a valid conclusion. Option D is also valid, since we know that most of the particles are deflected while only some of them are. Most of the particles are not deflected, they will go right through it, but only some of them are deflected away from the nucleus. It means that the nucleus is very small compared to the atom. Now for question 6, we have a negative charge and a positive charge placed close together of equal magnitude. A negative and positive charge will attract each other, so C and D are wrong. And we'll have field lines going from the positive to the negative. So option B is the correct answer. Now moving to question 7, we are given statements about cyclotrons. If we look over here, cyclotrons are basically particle accelerators like this. You have two Ds and the particles are going around like this and gets accelerated. So the particle goes around like this and is accelerated. A cyclotron needs the particle to be charged to accelerate them, so it cannot accelerate neutrons. A is wrong. A cyclotron uses electromagnetic field between the Ds to increase the speed. Cyclotrons do use magnetic field, but they use it to keep the particles in this circular motion around the Ds. When it's in the Ds, it's not accelerating, it's just moving in circles. And to keep it moving in circles, we need to give it a magnetic field to produce the centripetal force. But it does not increase the speed of the particles. Option B is wrong. Then in option C, we are told that it uses an alternating potential difference at constant frequency. This is the right answer. Cyclotrons use alternating potential difference since the object that they will accelerate has the same charge. So for example, if it's accelerating a proton, it's always positive. So it's attracted to the negatively charged side. So for example, this is the negatively charged side right now, it's attracted to this, so it will accelerate. But when it comes back here, it's still gonna be attracted to the negative side. If this side is still the negative side, it will not be accelerated. It will want to stay over here. It will want to stay over here if it's negatively charged. So we use alternating potential difference, which causes this to become negative when the particle reaches this point. This side will become negative and the particle will be attracted to the other side, causing it to accelerate. Now for option D is wrong because a cyclotron uses magnetic field to keep particles moving in a circular path and uses electric field to increase the speed. In question 8, we are given two non-relativistic particles of mass m and momentum p and kinetic energy Ek. And we are given a second non-relativistic particle of half the mass and double the momentum. We have to find the expression for the kinetic energy of the second particle. We know that the kinetic energy is half mv square and the momentum is m times v. In this case, we have no information given about the velocity. So from this equation, I'll take velocity as the subject. I'll get momentum divided by mass. Now I can put that in the equation for the kinetic energy. So Ek is half times m times p by m squared. This is basically p squared by m squared. I can cancel this m with one of the m's here. The kinetic energy is p square divided by 2m. P square is the momentum squared and it's divided by twice the mass. Now, in this case, the momentum is doubled. So on top we have a 2 square and the mass is halved. So on the bottom we have an m by 2. So the change is 2 square divided by 1 by 2, which is 8. So this was Ek. Ek is p square by 2m. Now the new Ek is 2p whole square divided by 2 times m by 2. I'll keep this over here. So before we go there, we have 4p square times 2 times m by 2. I can move this 2 to the top. I'll have 8p square by 2m. Now I can take the 8 out as common. I'll have p square by 2m. This was the previous kinetic energy. So 8 times the previous kinetic energy. So the new kinetic energy will be 8 times the first one. Now in question 9, we are given a ball that is traveling at a speed of u towards the wall and collides with the wall at right angles. So this is the wall and this is the ball. It's traveling at velocity u initially, and after colliding with the wall it travels in the opposite direction with speed v, and the collision time is given t. We have to find the average force on the wall. We know that force is also the rate of change of momentum. So the force is equal to the mass times v. So the change in momentum, so mv minus mu divided by t. Now in this case, the v and u are in different directions. So if I consider the rightwards motion to be positive, this is gonna turn out negative. So for this scenario, we have m times minus v minus mu. So minus mv minus mu divided by t. I can take m out as common. I'll be left with minus u minus v divided by t. Now we don't find that in the answers, so I can take a minus 1 out of here. So I'll have, if u plus v, I can take the minus out. Since it's wanting the average force, we can just find out the magnitude. We don't have to deal with this minus, so we'll be left with m times u plus v by t, which is option A over here. Now moving to question number 10, we are given a proton that is accelerated by a uniform electric field, and after t seconds the speed has increased by del v. Then we are told that a helium nucleus is accelerated by the same electric field. We have to find the time when the helium nucleus will have the same change in velocity del v. Now in this question, we know that the electric field strength will be the same, since this is a uniform electric field. The electric field strength, now we can relate this to the force. The electric field strength with respect to the, so I'll start with the force being equal to the electric field strength divided by the charge. Now if I make the electric field strength the subject, I'll be left with, the force is E times Q. The electric field strength is the force divided by the charge. Now I can write mass times acceleration in place of the force and the charge below. Now instead of acceleration, I can write it down as the change in velocity per time t divided by the charge. Now this is for the proton. Now for helium, the mass will be 4 times as before. E over here is still the same. Before we do that, I'll make T the subject. So I have EQ equals to m del V by T. So if I make T the subject, I am left with m times the change in velocity divided by EQ. This is for proton. Now for helium nucleus, the mass is 4 times before. So for T, I have the mass which is 4 times more than before. So 4m del V. The field strength is the same. The charge, however, is twice of the proton, so 2q. I can move the constants outside, so I'll be left with 4 by 2 here, and I'll be left with m del V E times q. This and this expression are the same, so the time taken for helium to accelerate is 2 times the previous time. So B is the answer. Now moving to section B. In the first question, we are given to state the difference between a proton and a positron and an electron. The difference is that a positron is positively charged and an electron is negatively charged, so they are oppositely charged. In part B, we are given a decay over here, and we have to talk about if it's possible or not using the conservation of charge and conservation of Lepton number. Now if I look at charge, the charge of the charge on the left is -1. This is a muon, and on the right we have -1 for the electron, 0 for the electron neutrino, and 0 for the muon antineutrino. So charge is conserved. Now if I look into Lepton number, the Lepton number of a muon is +1, the Lepton number of an electron is +1, the Lepton number of an electron neutrino is +1, and the Lepton number of an muon antineutrino is -1. So on the left we have +1, on the right we have 1 + 1 -1, so +1. So the same on both sides. So if I write it down like this, I'll write down the total charge on the left, the total charge on the right, the Lepton number on the left, and the Lepton number on the right. So we see that the charge on the left and charge on the right are the same, the Lepton number on the left and Lepton number on the right are the same. So from here we can draw the conclusion that this is possible since the charge and Lepton number are conserved. So this is how we give our conclusion that the charge on the left and the charge is conserved and the Lepton number is conserved, so the decay is possible. Now moving on to question 12, we are given a point charge placed at X, and we have to add lines to show equipotentials of equal potential difference. So they will be spheres. Since we have a 2D surface, we cannot draw spheres, we'll draw circles, and the circles will have increasing radius. So this is the first equipotential line. Try to have it in the center. The next one will be a bit further, so somewhere around here, and the next one will be even further apart. I don't really have enough space to draw the next one, so this will do fine. 3 is the minimum. You could usually do with 2, but it's safe to do 3 or more. Now we are given a charge of -4.5 nanocoulombs placed 4 centimeters from X. We have to calculate the magnitude of the force acting on this charge, given that the charge at X is 7 nanocoulomb. We know that the charge is F times K times Q1 times Q2 by R square. R is the distance between them. Q1 and Q2 are the charges and K is the constant. The value of K is given at the back of this question paper. Over here, K is the Coulomb's law constant, 8.99 into 10 to the power 9. So the force is K, which is 8.99 into 10 to the power 9 times the charge of X. So 7.0 into 10 to the power minus 9 times the charge of this, which is 4.5 into 10 to the power minus 9 coulombs. I don't really have to deal with the negative since we are asked to find the magnitude only. The distance between them is 4 centimeter. I'll convert it into meters and square it. The force will come out to be 1.7699, so 1.77 into 10 to the power minus 4 newtons. This is the magnitude of the force. Now for part C, we have to find the work done when moving this 4.5 nanocoulomb charge from a distance of 4 centimeter from X to 9 centimeter from X. So this was particle X, positively charged particle, and the other particle was negatively charged, and it was 4 centimeters from X. Now it's moved away from X to 9 centimeters. So work was done against the electric field. We have to find that work done. Now we have to use two equations. We know one equation from here, that V is KQ by R square. Here the value of Q is the charge of the 4.5 nanocoulomb. So Q2, we can write this down as Q2 since we are considering this to be Q2. Q1 over here is 7 nanocoulomb, so the charge of particle X. Now now we can also link the voltage with the work done. So the definition of voltage is the energy stored per unit charge. So it's W divided by Q. Now this Q over here will be Q1, the charge of the positive one, so the charge of X. Now I can make the work done the subject from here. The work done will be V times Q1. We know that V is this expression over here. So the work done will be KQ2 by R square. Sorry, this is R. V is KQ2 by R. So the work done is KQ2 by R multiplied by Q1. So the work done over here, I'll not directly place in the values. I'll find the difference between the work done when it's 4 centimeter away and 9 centimeter away. So when it's 4 centimeter away, it's 8.99 into 4.5 into 10 to the power minus 9 divided by R, which is 4.0 times 10 to the power minus 2. Then I subtract the 1 for 9 centimeters, so 9 into 10 to the power minus 2. On the numerator I have 8.99 into 4.5 into 10 to the power minus 9. I multiply this change with Q1, which is 7.0 into 10 to the power minus 9. If I calculate this, I get a value of 3.93 times 10 to the power minus 6 joules. Now there might be a confusion on why we have to do this. This value over here, this potential difference, will only show the potential difference exactly at that point. But in this case, I want to find the difference between them. So the difference from here to here. So for that difference, I'll first find the value for this point and then find the value for this point and then subtract them from each other. And if I multiply it with 7 into 10 to the power minus 9, we'll get the work done. If we think deeply about this, we'll have the change in work done equal to kq2 by r q1. So the change in this value. The other ones don't change, just the value of r changes. So we basically had 8.99 into 10 to the 8.99 into 10 to the power 9. Oh, I missed that over here. We have the 10 to the power 9 over here. So this is the correct expression. I just missed the 10 to the power 9s while writing it down. Don't worry, it was included in the calculations for this. This value is right. Now if I look over here in the red, we basically had that difference when it was 4 centimeters away. So this was when it was 4 centimeters away. So the work at 4 and the work at 9 was the same expression, just taking the denominator as 9 into 10 to the power minus 2. In this expression over here, we just took out the 7 into 10 to the power minus 9 out as common when we did W4 minus W9. So that's what we did over here. Now for question 13, we are given the forces acting on an aeroplane over here. We are given that the lift force is perpendicular to the wings, and then we are told that to change the direction, the aeroplane bangs. So basically the bending of the aeroplane or the rotation, where one wing is lower than the other and the lift force is no longer vertical. This lift force will then provide a centripetal force. Now we are given that the aeroplane flies in a horizontal circular path at a velocity of 52 meters per second at a speed, and we have a banking angle of 20 degrees. We have to find the radius of the circular path and show that it's about 800 meters. Now the horizontal component of lift, this one over here, will provide the centripetal force. So this will be equal to mv square by r. Now using the fact that this blue line and this dotted line over here are parallel, we can find this angle is also 20 degree. They are alternate angles, and this whole angle is 90 degrees. So this angle over here is 90 minus 20, which would be 70 degrees. So this force over here, the blue one, will be the total lift times cos 70 degrees. And the vertical component of lift, this one will be the lift times sine 70 degree. In place of cos 70, we could have also used sine 20, and in place of sine 70, we could have used cos 20, but you don't have to go into detail for that. Basically, in that case, we could have just found out that this angle is also 20 degrees, since this over here is a 90 degree, but you don't have to go so far. Now we know that the mass of the aeroplane is 1200 kg. So this downward force is 1200 kgs. So 1200 g. The lift will balance the downward force. So 1200 g is equal to the lift times sine 70. From here I can find the value of the lift. The lift is 1200 g divided by sine 70. So if I place the value of g, which is 9.81 over here, and I calculate this, I'll get a value of 12,500 27.5 newtons. This is the lift force. Now the centripetal force is L cos 70. So L cos 70 degrees is equal to mv square by r. Now we know the mass and the velocity. The mass is 1200, the velocity is 54. I just have to find the radius. We also know the value of L, this is 12,527.5. Now I'll just find the value of R, which will be 1200 multiplied by 54 square divided by 12,527.5 cos 70 degree. You also could have used the exact values of L to calculate this. The value of R comes out to be, if we calculate this, the radius comes out to be 817 meters, which is close to 800 meters. Now for part 2, we have to determine the time taken to move 90% on 90 degrees of its circular path. Entire circular path is 360 degree. 90 degree is a quarter of a circular path. So if the total circular time path takes t, this part over here will take t by 4 seconds, since it's a quarter of the entire circle. I can find the period or the time period over here, since I know the speed, the radius and the force. The velocity over here, v, will be 2 pi r by t. Basically it comes from the fact that the angular velocity is 2 pi by t and v is omega r. So if I multiply r on both sides, on the left I'll be left with v, and on the right I have 2 pi r by capital T, or the time period. I can make the time period the subject. On the top I'll have 2 pi times 816, our answer 817, our answer from the previous question, divided by 54. So the time period is 95.025, so 95.03 seconds. So to move 90 degree, the time taken will be capital T by 4. So 95.03 divided by 4, which comes out to be 23.8 seconds. So it takes 23.8 seconds to move 90 degree. Now in part B, we are told that the wings are now leveled off and the speed and magnitude of the lift force remains the same. We have to talk about what happens to the vertical motion of the aeroplane. If the lift remains the same, previously the lift times sine 70 was more than the weight. So in this case we have the lift, which is 12,527.5. The weight is 1200 g, which is only 11,772 newtons. So now the weight is less than the lift, so the upward force is more than the downward force. So there will be a resultant upward force causing the plane to move or accelerate upwards. So this is how we write it down. We tell that the lift is more than the weight, causing an upward resultant force which causes it to accelerate upwards. Now on to question 14. We have to state the principle of conservation of momentum. We have to remember this. We are given 2 marks over here. The first is the mark about the fact that we talk about the total momentum before a collision or an explosion is equal to the total momentum after the collision or explosion. And the second point, the second mark, which is commonly missed out, is the fact that we have to talk about that the thing has to occur in a closed system, or there has to be no external forces on it. For example, if a car was moving along a rough surface, it will lose its speed if it did not have a engine on, it will automatically come to rest simply due to the fact that friction is over here. Friction is an external force over here. So we have to state that there cannot be any external forces in this case. So this is how we write down our answer. We talk about the total momentum before a collision or explosion being equal to the total momentum after the collision or explosion, given that there are no external forces. Now we are given this spreadsheet over here for the initial values and the final values of the masses, the velocity, and the angle of the direction of motion. We have to find out if this shows that there is an elastic collision. Now, if it is an elastic collision, the kinetic energy is also conserved. If it's an inelastic collision, we have the momentum will be conserved in an inelastic collision as well, but the kinetic energy won't be. So we just have to show that the kinetic energy is conserved in this case. So the initial kinetic energy, since the velocity of object B is 0, initial kinetic energy is equal to half times the mass over here, which is 0.85 times 1.3 square. So the mass 0.85 times the velocity 1.30 squared. The initial kinetic energy comes out to 0.71825 joules. The final kinetic energy should also be calculated. This is half into 0.85 into 0.98 square plus the kinetic energy of object B, which is half times 1.7 into 0.45 square. If I calculate this, this will come out to be quick correction. This is 1.7 and this is 0.54. And if I calculate this, we get a value of 0.65603 joules. Now this is different. The initial kinetic energy is greater than the final kinetic energy. So the kinetic energy is lost over here. It's not conserved. So this is an inelastic collision. So we draw our conclusion over here that it's not an elastic collision, since initial kinetic energy is more than the final kinetic energy. Now we have to show and deduce that these values show the conservation of momentum. With energy we could work without considering the angles. We just had to work with these two rows over here. We only had to work with rows 3 and 4. Now in case of momentum, I'll also have to think about the directions. Initially the momentum was only to the right. So this momentum was the initial momentum, which is 0.85 times 1.30. So mass times velocity. This is 1.105 kg meter per second. This is the initial momentum and it's all to the right. It's entirely to the right. And if I work with the final momentum, I need to work out this angle. This angle is 54.5 degrees. And if I want to work out this angle over here, it's 48.0 degrees. Now in the case of this, so before the collision, the vertical momentum was 0 kg meter per second, and the horizontal one was 1.105. So after the collision it should also be the same. Both of them will have a rightwards component of momentum. For this, it's this entire expression, so mass into velocity times this will be cos theta. So if I have the P, so this is final, So this is PA after collision. This is 0.85 times 0.98. We get a value of 0.833 kg meter per second. For B, the momentum after collision is 1.70 times 0.54, which is 0.918 kg meter per second. The horizontal component for this will be 0.918 cos 48. The vertical component will be 0.918 sin 48. And over here, the horizontal component will be 0.833 cos 54.5. The vertical one will be 0.833 sin 54.5. Now finally we have the upwards momentum. This is 0.833 sin 54.5 minus, since this is in the opposite direction, 0.918 sin 48 degrees. This value when calculated comes out to be minus, so this is downwards. I'll change this arrow over here as well, since it doesn't really matter since it's 0. This is okay, then this is flipped, so this is positive and this is negative. Upwards is negative. This value will come out to be 0.00405. This is almost 0. And if I want to find the momentum component to the right, this is the addition of this term and this term. We have 0.833 cos 54.5 plus 0.918 cos 48. This comes out to be 1.097. So 1.098 kg meter per second. This is the final momentum towards the right. This value over here is 1.1. So this value is almost 1.1 approximately. This is also 1.1 approximately. So we can draw a conclusion that the momentum is conserved since the initial momentum and final momentum are the same. So we begin by mentioning that the momentum before collision is equal to momentum after collision. We have to talk about both directions. So left, right and up, down in both directions. So we have the momentum before collision equals to momentum after collision in all directions. So we can say that the conservation of momentum is demonstrated over here. So we finally say that the conservation of momentum has been successfully demonstrated. Now moving to question 15. So this is our 6 marker over here. We are told that a student placed 2 magnets on a holder so that the north pole of one magnet faced the south of the other, and this was placed on a sensitive balance calibrated to measure force. And then the student held a closed loop of wire between the magnets. And in this question we are told that when the student moved this wire quickly downwards between the magnets, the reading of the balance changed. We have to explain how it changed. So here we have to talk about Lenz's law and Faraday's law. We have a conductor moving in a magnetic field, so it will have induced current on it, induced EMF on it due to it being a conductor moving through a magnetic field. It will experience a change in flux cut. So the flux linkage of this wire over here will change when it's moving down the magnetic field, which will cause an induced EMF in this wire. The induced EMF will cause the wire to have a current in it, and according to Lenz's law, this will oppose the direction of motion of the wire. Since if we are moving the wire downwards, the Lenz's law force will provide a force on the wire upwards. If there is an upward force on the wire, there must be a downward force on the magnet according to Newton's third law. So the balance reading will increase. So we'll write that down over here. So we write down this. We write down when the wire is moved between the magnets, there is a change in flux linkage of the wire. This induces an EMF in the wire, causing a current to form in that. And this current is in a magnetic field. So it will experience forces according to Fleming's left hand rule. And according to Lenz's law, this force will be upwards. This will oppose the downwards motion of the wire, and hence it will be upwards. And then we can apply Newton's third law of motion, saying that there will be an equal downward force on the permanent magnets, causing the balance reading to increase, since the balance reading will now give the value of the weight plus this additional downward force. Now for part B, we have a voltmeter that was connected across the ends of the second wire, and then this wire was moved vertically downwards between the magnets at a constant speed. And we're told that a potential difference was observed while the wire was moving. We have to calculate the maximum potential difference that could be measured. We have the length of each magnet, the height of each magnet, the flux density between them, and the vertical speed. We know that the EMF induced is equal to d phi by dt. So this is equal to d times nba. Here the value of n is 1, so we have the d times ba by dt. Now the EMF is, b is a constant, so I'll write it outside. So we have b times dA. A over here is the length multiplied by the width, or in this case the height, divided by dt. The EMF is b times, the length is also fixed, so b times L times dH by dt. Now dH by dt is how fast the wire is moving down the magnet. So this is h, and the velocity is how fast it's moving down. So dH by dt is the same thing as the vertical speed. So the EMF is b, which is 0.35 multiplied by L, which is 34 millimeters, so 34 into 10 to the power minus 3, times the velocity, which is 2.2. The maximum potential difference is equal to 0.02618, so 0.0262 volt. Now we have question 16 about capacitors. The student planned to use this circuit over here to measure the potential difference across the capacitor as it was charged and discharged through resistor R. So if I consider the switch being at X, this is when it's discharging. Oh, sorry, the cell is over here. This is when it's charging. However, when it's charging, this is the complete loop. So this over here is the complete loop. The voltmeter is not in this. So when it's charging, the voltmeter is not connected. And when it's discharging, this is the complete loop. Now in this case, the resistor is not connected. So these are the two issues with the circuit. These are the two reasons. So in this case, we talk about how when the switch is at X, the voltmeter is not across the capacitor, and when the switch is at Y, this point, the resistor is not in the circuit. Now we'll move to part B. Here we are given a graph of the voltage against time after we move from position X to position Y. Position X was the charging circuit and position Y was the discharging circuit. We are given the capacitance of the capacitor C. We have to find the resistance in the circuit. Now I can use the time constant to do this. The time constant is the time it takes for the initial voltage to become 1 ETH. So 1 divided by E, which is around 38%. So the initial voltage, if I want to find that, now I see that each 5 box, so 1, 2, 3, 4, 5, each 5 box represents 1 unit in the y-axis. So each small box represents 0.2 volts. So this is 6, this is 6.2 volts. Now 6.2 divided by E is 2.28. So 6.2 divided by E, this is 2.28 volt. So this is 2.2, this is 2.4. 2.28 is somewhere in between, around here. This value is at this point. Now in the x-axis, each 5 box represents 5 seconds. So each box represents 1 second. So this is 21, 22, 23, 24 seconds. So the time constant RC, T equals to RC, is equal to 24 seconds. I want to find the value of R, and the value of C is 2.2 microfarads. So 2.2 into 10 to the power minus 6 farads. So the value of R will be 24 divided by 2.2 into 10 to the power minus 6, which comes out to be 1.09 into 10 to the power 7 ohms. This is the resistance. Now for part 2, we have to find the average current between t equals to 0 and t equals to 30. The average current will be the change in charge divided by unit time, or divided by 30 seconds in this case. Now the charge is equal to the capacitance times the voltage. Now at 0 seconds, the voltage was 6.2 volts. So we have Q equals to 2.2 into 10 to the power minus 6, this is fixed, times 6.2. This value comes out to be 1.36 into 10 to the power minus 5 coulomb. And at 30 seconds, the charge will be the capacitance, which is 2.2 into 10 to the power minus 6, times the voltage at t equals to 30. We have to find this. So at t equals to 30, we have this value over here. This corresponds to 1.8. So multiply 1.8 over here. This was 6.2. This comes out to be 3.96 into 10 to the power minus 6 coulombs. So the change in charge is 1.36 into 10 to the power minus 5 minus 3.96 into 10 to the power minus 6. This comes out to be 9.64 into 10 to the power minus 6 coulomb. And to find the average charge, I'll just divide this by the time it takes. So divided by 30 seconds, this comes out to be 3.23 into 10 to the power minus 7 amperes. Now we have to calculate the energy dissipated by this current between time equals to t equals to 0 and t equals to 30 seconds. The work done by a capacitor is given by half CV square. Basically we have half QV as the formula, but we know that Q equals to CV, so if I just replace that, I'll get half CV square. I'll use this over here. Now the change in work done is the energy dissipated between t equals to 0 and t equals to 30. So half C is constant, so half into 2.2 into 10 to the power minus 6 is the same for both. And then we'll have 6.2 square minus 1.8 square. We could do this like we did for this question. So at time equals to 0, I'll find the work done at this point. This will be 6.2 square, and then find it for t equals to 30. I'll just change the value of the voltage. The energy dissipated will be the first value minus the second value. So half into 2.2 into 10 to the power minus 6 into 6.2 square minus this whole thing again. So I can just take this out as the common, and I'll have 6.2 square minus 1.8 square. This value comes out to be 3.87 into 10 to the power minus 5 joules. Moving to the penultimate question. We have an apparatus over here containing an anode, a cathode, metal plates. We are told that a potential difference was applied across the metal plates, producing an electric field between them, and a magnetic field of flux density B was applied at right angles to that field, and that electrons were emitted from the cathode and accelerated towards the anode and moved between the metal plates at a speed of v. Then we adjusted the value of the magnetic flux density until the electric and magnetic forces on the electrons were equal and opposite, and the electrons passed between the metal plates in a straight line. Now we have to show that this is the velocity of the electrons. For the magnetic and electric forces to be equal and opposite, they must have the same magnitude. So force due to magnetic field and force due to electric field must be equal in magnitude. So BQV is equal to EQ. E is the electric field strength, B is the magnetic flux density, Q is the charge, and V is the velocity. We can cancel out the charge on both sides, and then if I make V the velocity the subject, I'll be left with the electric field strength by B. Now we also have to convert this electric field strength to the potential difference. Now the link between the electric field strength and the potential difference is that the electric field strength is equal to the potential difference divided by the distance. So I can replace that over here. I can replace E with the potential difference divided by D. The whole thing is divided by B. So the velocity is equal to the potential difference divided by the magnetic flux density times the distance d. We have shown that this equation is the speed of the electron. Now we are given an experiment using similar apparatus. We have to show that the value of V is 3 into 10 to the power 7 given the other values. So we'll just use the equation we had. The velocity is V, which is 231 volt. This V is the capital V, divided by 5.5 into 10 to the power minus 4, which is the value of B, and then the value of small d, which is 1.5 centimeter. I'll have to convert this into meters, so multiply 10 to the power minus 2 with it. The velocity comes out to be 2.80 into 10 to the power 7 meter per second, which is really close to 3 into 10 to the power 7. Now for part 3, we are told that when the electric field between the plates is switched off, the electrons move in a circular path of radius 39 centimeter due to the magnetic field, and that the accepted value for the charge per unit mass is 1.8 into 10 to the power 11 coulomb per kg. We have to deduce whether the charge per unit mass of an electron calculated using data from the experiment is consistent with the accepted value. The charge per unit mass is basically Q divided by M. So I have to find Q divided by M for this case. Now we know the magnetic field strength over here, the radius of the circular path. It's gonna be in a circular motion, and the magnetic field will provide the centripetal force. So we have the force of magnetic field providing the centripetal force, so mv square by r. So bqv will be equal to mv square by r. I can cancel a v from both sides. I'm left with bq equals to m by r. I want to make q by m the subject, so I'll move the mass to the left. So I'll have q by m on the left. I'll move the b to the right. So on the right, I'll be left with v divided by br. Here the value of q by m will be the velocity that we calculated in the last question, which is 2.8 into 10 to the power 7 divided by b times r. B is 5.5 into 10 to the power minus 4, while r is 39 centimeters. So 39 into 10 to the power minus 2. The value of q by m comes out to be 1.305, so 1.31 times 10 to the power 11 coulomb per kg. The accepted value is 1.8 into 10 to the power 11, while this is 1.31 into 10 to the power 11. This is much less than the accepted value. Now moving to part B, we are given a beam of electron that is directed at the thin films of metal, and this is the pattern that we are observing. We have to explain how this pattern changed scientists' understanding about the nature of electron. This thing over here is a diffraction pattern, and this only occurs for waves. Before this, we thought that electrons only behaved as particles, but this result shows that, or this observation over here shows that electrons can also behave as waves. So we talk about how this diffraction pattern should only occur for waves, and hence this observation shows that electrons can behave as waves as well as particles. Now for the last question, we have a question about the quarks. So we are told that in 1977 a fifth quark named the bottom quark was discovered by physicists, and this is the table of known leptons and quarks at that time. From this, scientists predicted the existence of a sixth quark over here. We have to explain why they predicted this. If we look over here, the up and down quarks are a pair, the strange and charm quarks are a pair. So from here, according to symmetry, we can predict that bottom quark will have a quark that's a pair to it. So these are pairs, these exist as pairs, these two exist as a pair. So the bottom quark must have something else that it exists as a pair with. So this is how we structure our answer. We first talk about the first generation quark up and down being a pair, strange and charm in the second generation being a pair. So this over here, this empty space should be filled with something that's in pair with the bottom quark, and we can predict this due to the standard model being symmetric. Now for part 2, we have a question. We are told that a short time after formation, most quarks combine to make particles known as hadrons. We have two categories of hadron. We have to name them. The two categories of hadrons we know are mesons, where we have one quark and another antiquark, and baryons, where we have three quarks together. So a proton is a baryon, for example, neutron is another baryon. Now to part B, we are told that the sixth quark was known as the up quark, was discovered in 1995 with a collision of a proton with an antiproton. Then we are told about particle experiments that may direct beams of particles at stationary targets or collide beams of particles traveling in opposite directions. Now we have to explain the advantage of colliding beams of particles. So the second one, not stationary targets, we are talking about the advantage of colliding beams of particles moving in opposite directions. We have 4 marks for this. The advantage is that if something is stationary and you hit this, if you think about momentum, there is a resultant rightward momentum before the collision. So after the collision, there must be a resultant rightward momentum. So the products must have kinetic energy after the collision. So sum of its energy should remain as kinetic energy. So this is a loss of energy. We want everything to be converted into mass. We want all of the energy being converted into mass. However, in this case, we have to let some of the energy turn into kinetic energy. However, if we have another one moving in opposite direction, the resultant momentum can be 0. So the final momentum, the initial momentum over here is 0. So the final momentum will also be 0. So all of the energy can be converted into mass. So we write down that if the beams collide, there is a resultant 0 resultant momentum, and hence the products may have close to 0 momentum after the collision. If that happens, they will have very low or almost 0 kinetic energy after the collision happens. So all of the energy is available to form particles. So more heavy particles can be produced in this scenario. Now we are given a calculation question where we have to calculate the maximum kinetic energy of a top quark produced in the experiment when a proton and an antiproton of total energy 900 giga electron volt each collides. We have the rest energy of the top quark being 173 giga electron volts. So the kinetic energy over here will be 900 minus 173. In this case, you can think that the total energy before collision was 900 times 2. However, the rest energy of top quark will also be doubled in this case, because when a proton and antiproton collide, we produce a top quark and a top antiquark as well. Both of them have the same mass. So the kinetic energy, or max K in this case, is 900 times 2 minus 173 times 2 divided by 2. Basically 900 minus 173 giga electron volt, which is 727 giga electron volt. Now I just have to convert this into joules since they want the answer in joules. So 727 giga electron volt is 727 into 1.6 into 10 to the power minus 19. This is converting electron volts, and we had a giga electron volt, so I'll have to multiply 10 to the power 9 as well. From here we get a value of 1.16 into 10 to the power minus 7 joules. Now for part 3, we have to deduce whether a top quark with a kinetic energy of 1.2 into 10 to the power minus 7 is traveling at relativistic speeds. First I have to find the mass of the top quark in kgs. Since I want to find, I know the kinetic energy, I want to find the velocity. For this I need the mass as well. So I need to convert this mass over here from giga electron volt per c square to kilograms. To do so, I'll have to do some calculations over here. So I'll have 173, this is giga, so 10 to the power 9. Now converting the electron volts into joules, so 1.6 into 10 to the power minus 19, and I have this divided by c square, so 3 into 10 to the power 8 whole squared. This is equal to 3.08 into 10 to the power minus 25 kilograms. This comes from the equation E equals to mc square. So from here m is basically E divided by c square. Now I know the mass and the kinetic energy. I know the kinetic energy in joules, which is 1.16 into 10 to the power minus 7. This is half times the mass, which is 3.08 into 10 to the power minus 25 times v square. I'll calculate the value of v. V is 1.16 into 10 to the power minus 7 divided by half into 3.08 into 10 to the power minus 25. This is v square. So I take the root over of the right. This is the value of v. This comes out to be 8.70 into 10 to the power 8 meter per second. This is greater than the speed of light, so this must be so this is not a relativist. This is traveling at a relativistic speed. This is not traveling at this speed. This is not possible. Anything in this universe cannot travel at speeds greater than 3 into 10 to the power 8, which our calculations say it's doing. For any questions where we have to show that a particle is traveling at relativistic speed, we have to show that its calculated velocity is greater than the speed of light, and vice versa. If we have to show that it's moving at non-relativistic speeds, it will have low velocities, not close to the speed of light. Now for the last part, we are told that most types of quark form hadrons on a time scale of 10 to the power minus 23 second, and the top quark does not form hadrons because its lifetime is only 10 to the power minus 25 second. A student suggests that if the top quarks travel at relativistic speeds, it could be possible for them to form hadrons. If the top quarks moved at high enough speeds, the lifetime would appear to increase to outside observers. However, if that's the case, it would also take a long time to form the hadrons with respect to external observers. So if I am observing a hadron being produced from top quark, which is moving at high speeds, I am watching this top quark move on and on for ages, but it's not gonna do anything since it's perceiving times faster than me, or it's perceiving time slower than me. So if it has been 5 hours for me sitting there, it hasn't even been 10 to the power minus 99 seconds for this top quark, because it's moving at relativistic speeds. So this would also increase the time for the hadrons to form. So this suggestion would not be possible. So the main issue is that it takes 10 to the power minus 23 seconds to form a hadron, while the top quark only has a lifespan of 10 to the power minus 25 seconds. Now, even if it's moving at relativistic speeds, the time that it thinks has traveled for himself, or the lifespan according to the quark's perspective, is still 10 to the power minus 25 seconds. The quark needs 10 to the power minus 23 seconds with respect to himself or itself. So from its own perspective, the quark needs to last at least 10 to the power minus 23 seconds to form a hadron by looking at time from its own perspective. If I am observing externally, maybe the time that lifetime has increased to 5 hours for the quarks, but if that happens, it will take 7 hours to form hadrons. So 5 hours is the lifespan and 7 hours is the time needed to form hadron. So even then, the quark will not have a lifespan which is long enough to form a hadron. So this is how we answer it. We talk about how external observers will see an increased lifetime, but its lifetime would not increase from its own perspective. So its lifetime will be shorter than the time needed to form hadrons, even if it's moving at relativistic speeds, making the statement incorrect. And that's it for this paper.